So this anatomy and physiology video looks at muscle fibres, the different types of muscle fibres that you might find in any muscle, and most importantly how the different muscle fibres are structured and how this links to the function that they have or the job that they do. But let's firstly look at this image actually, because it tells us quite a lot of information. So this is our typical muscle and the muscle belly, the large structure. This is a skeletal muscle, and what you can see here in this cross section is that it's not just one solid muscle. We've actually got bundles of individual fibres. So this here picks out one bundle, and then what you can see from this bundle is that we have individual muscle fibres all made up of very tiny proteins called myofilaments. But for our purposes we need to just recognise here that we have different types of muscle fibres. We have slow twitch or fast twitch muscle fibres, and what they've done is they've used a different colour to show the different types of what we call motor units. So we've got here from the spinal cord, our brain would obviously send a message down the spinal cord, and this would travel down the nerve right the way to the nerve endings, where it would pass on the information telling this muscle fibre to contract. Now the message coming from the spine down the nerve, you can see there's a division here. This goes down to this nerve muscle fibre and down to this muscle fibre. And this nerve and those two muscle fibres that it controls is called a motor unit. So here we've got a slow twitch motor unit, and here we've got a fast twitch motor unit. Now this motor unit has 1, 2, 3 connections or 3 fibres that it controls. So it's a slightly larger motor unit, which is quite typical of fast twitch and slow twitch units. Fast twitch tend to be a little bit larger. So from here then we know that nerves and nerve impulses within a motor unit control the muscle fibres connecting to that nerve, and we know that individual fibres make up a bundle, and several bundles make up an actual muscle. So looking at these images here, you may again know from GCSE that we have different types of muscle fibres. There are actually 3 types of muscle fibres. What type of fibre do you think would be predominant in his muscles, this endurance athlete Mo Farah? Well, the answer is slow oxidative muscle fibres. You might know them as slow twitch fibres, but yes, slow oxidative, and the clue is in the name, slow and oxidative, oxygen. There, we'll talk about the properties of these fibres in a little while. What about down here then? So we've got a sprint athlete, and you can look at the difference between the musculature of these two typical types of athletes. Sprinters tend to be quite, very powerful, big muscles. Endurance athletes are muscular, but it's smaller musculature. So the fibres that the sprint or explosive power athletes would have would be more fast glycolytic fibres. Again, you might know these as fast twitch, and again that perhaps the clue is fast and glycolytic, glycogen. And I've got a football player here. Now it's not so much the action of kicking that's important, it's the flexibility that a footballer requires. They're required to sustain contractions for 90 minutes or more, and they're required within that to sprint, to kick, to jump, power activities also. So the muscles of this type of performer wouldn't need to be completely that or completely that, but need to be quite a mix. And I've put this as an example of fast oxidative glycolytic fibres. These, as you might tell, combine some of the properties of these two extreme type of fibres, but we'll look at that in more detail. You need to realise, if you don't already, that we determine our fibres. So you might be born with, based on your parents' genetics, a high proportion of slow oxidative fibres, and what that means is you're possibly going to be quite decent at endurance events, or you might be born with a high proportion of fast glycolytic fibres, in which case you might be potentially good at power or sprint or explosive activities. But we're all born with a mixture of these 3 types of fibres. So they have different jobs and they work in different ways and they are built slightly differently. So we're looking in this graph at the number of motor units that are recruited, that are called upon to work during light, medium or heavy workloads, and we're also looking at the amount of force that these motor units can generate, so how powerful the contractions are. The first motor units to be recruited during light work would be slow oxidative fibres. So when you're not working particularly powerfully, when you're doing gentle work, for example during a warm-up, you would call upon your slow oxidative fibres to work for you to make your muscles contract. They don't generate particularly high forces relative to the others, but they can go for a long time. So slow oxidative fibres, generally speaking, have the least force production but the greatest level of endurance and aerobic capacity. They can keep going for a good while. During medium workload then, we might ask our fast oxidative glycolytic fibres to help out. Now our slow oxidative fibres would still try to work, but we need some additional help here from our fast oxidative glycolytic fibres, and they can generate slightly higher forces. So they can keep going for a good while, so they have moderate force and moderate endurance properties, so they can kind of do a bit of both. And then finally, when we get onto our heavier, more demanding, more powerful workload, our slow oxidative fibres try to help, our fast oxidative glycolytic try to help, but our fast glycolytic motor units would be recruited or called upon to work. And they, as you can see, generate the biggest forces that we can, but they can't do that for very long. So they have high force production, but low endurance capability. So the general rule of thumb of thinking about these fibres is how they are built, or the structure will link with the job that they have to do or the function, and you need to be able to make connection between those two things, and then ultimately those will be used to do the various motor skill performances that we do in our sport. For example, if fibres, so our slow oxidative fibres, have lots of mitochondria, and these are the cells which make energy using oxygen, these slow oxidative fibres therefore have a high aerobic capacity function, i.e. they can make lots of aerobic energy. So the more mitochondria your slow oxidative fibres have, the better they are at doing their job making energy using oxygen, which means that we as a performer can keep contracting for a long time, perhaps during a 10,000 metre run. So we have high endurance capacity. So again, let's look at the three different kinds of fibres in terms of their structure and function. And you might find that you need to pause the video to have a closer look at these, because there's a fair bit of information. So the function of fast glycolytic fibres, they are mainly for high intensity, low duration activities, speed, power, strength. They're the third in the order of recruitment. They have the highest contractile strength, so they can generate the biggest forces. They're the quickest contractors, so they contract quite quickly. They have the highest fatigability, so they get tired because of lactic acid build-up very quickly. They have the lowest aerobic capacity, so they don't really use oxygen, but they can work anaerobically really well. So that's the job, that's how they work, and we just need to look at, so how are they built to be able to do those jobs? And here's our table. So white in colour, large, they're very thick fibres, there's lots of them in a motor unit. They don't have very much myoglobin or mitochondria or capillaries, because these three things are important for aerobic work, and we know that they do anaerobic work best and not aerobic work very well. And they have high fuel stores, so the energy they use will be ATP and phosphocreatine to enable them to work anaerobically. So you can see there are connections between the structure, how they're built, and the way they work. How they're built, what they have, and the way they work. How they're built and the way they work. Slow oxidative fibres, then similarly you make connections. So here are the structural characteristics and the functional characteristics. So these are designed for posture, high duration, keep going for a long time, but low force, low intensity. They're first to be recruited, they don't generate big forces, they're quite slow to contract, but they don't get tired very easily, they can keep going for a long time. They work aerobically and not particularly anaerobically, so they have a different function. Consequently, they're built differently to do this different job. So they're quite small or narrow fibres. There's very few in motor units compared to the 800 in fast glycolytic fibres. They have high characteristics of these aerobic factors here, myoglobin, capillaries and mitochondria, and they don't have that much phosphocreatine, which is more of an anaerobic fuel. So again, make the connections between the way they're built linking to the job they do, the way they're built linking to the job, the way they're built linking to the job. Finally, fast oxidative glycolytic fibres. These guys kind of have the capability to work both aerobically and anaerobically. So they have anaerobic function and a reasonable aerobic function. They have moderate fatigability, moderate speed, moderate or quite high force. They're second to recruit. So these are called upon to help out the fast glycolytic or to help out the slow oxidative. And again, there are connections between how they're built and how they work, how they're built, how they work. You will need to be able to give structural characteristics and functional characteristics of all these three types of fibres. So we've covered a lot of information quite quickly here. As I said, you might want to pause the video and have a closer look at these. So slow oxidative fibres, fast or FOG fibres and fast glycolytic fibres, with a little bit more information in terms of structural and functional characteristics. Just very, very quickly then, we can train to make our fibres get better. So this image here shows you some of the effects of aerobic and endurance, or anaerobic and aerobic training. Firstly, remember that a lot of our fibres are determined genetically, so you can't necessarily make dramatic changes to the proportions that you're born with. You're born with it and that's it. But there is a nurture factor. We can train what we've got to become better. We can't make massive changes, but we can train them to do their job better. So looking at anaerobic training first, if you do lots of sprint training, power training, strength training, you can increase the number of fast glycolytic fibres, which is called hyperplasia, and you can also increase the thickness of those fast glycolytic fibres. That's called hypertrophy. So you know that if you go to the gym a lot, you get bulkier muscles, and that's because your individual fibres have become thicker, which is called hypertrophy. If you do lots of endurance training, what you can do is convert your fast glycolytic fibres to function as fast oxidative glycolytic fibres. So you're basically increasing their potential to work aerobically. You don't totally swap them to slow oxidative, but you can convert them to fast oxidative glycolytic, so manipulate them a little bit. And obviously you then make your aerobic slow oxidative fibres work better. So remember that you need to know structural characteristics and separately functional characteristics of all three of the types of muscle fibre. So make sure you can link how they're built to the job they need to do.